So the keynote reporter with and seat. And please be quiet and have a seat. So now let's start the second part. And as requested by the reporter, they will have the 5 minutes to prepare the presentation. So each team please write the name of the representative on the blackboard. 不要写那么长。哦，不要写那么长。要写正的，大家看得懂。
我很期待。
你写在旁边下面。对。
From Team Black Rangers, and today I'm going to report on TYP problem number 13, which is spaghetti accelerate. And this is our outline. So first of all, we'll start with the problem statement. When a piece of spaghetti is pushed into a dense tube, small debris of spaghetti may be ejected from the other end of the tube at a surprisingly high speed. Investigate the phenomenon. So our key questions emerge. First of all, why does spaghetti break? Second, what makes the ejected speed so high? And third of all, is there anything special about the debris? Okay, for the observation video, as you can see over here, the spaghetti will break and get out. And so now, let's talk about the braking mechanism. First of all, we assume that it's buckling. And so these are the equations that we applied. And then, for an experiment setup, so we use a Pascal force sensor where we can record the minimum force to break a spaghetti in different length. Then we can now calculate the constant EI mentioned earlier over here. And also we use a fixed side to act as a constraint body. And now for the buckling assumptions, it would be linear. However, the real data differs from the theory's assumptions. And also the error bars tend to be increased. And so, as you can see over here, after the certain point, the small, which is the small length part, the system will not stay towards the buckling theory. And also, this is what I said earlier, the significant variations. And so now, let's talk about a buckling analysis, where we only intercept, or actually we only take the small part of the previous slide, which is the linear part for the analysis, where we can calculate the slope, and we can calculate the buckling system. But it fails to provide a complete perspective, as it only discussed about the part that includes buckling. And now, let's talk about the theory of fracture. So the fracture is defined here. The strength of the material is influenced by internal defects like microcracks, whose size and distribution vary randomly. As the stretch required for crack propagation is reached, a chain reaction of fracture occurs, and stretch follows the probabilistic distribution. And as you can see over here, as we mentioned earlier, we assume it's buckling, where you can see it's like this. However, if for fracture, when it occurs at a smaller length, it will actually break into small pieces instead of having such buckling effects. And so this is the one that we use for the discussion, where as you can see over here, this is the point of fracture, where this part, because the lower initial force required, fracture will occur. However, for this part, which is at a longer length, due to a lower initiation force required, buckling will occur instead. However, for this part, it will not eject as this one because of the energy. And so as you can see over here, these are the comparisons of the theories. And so now let's talk about the linear elastic theory, where as we can see over here, this is sigma over E equals to epsilon. And for a strain energy density, we can provide an integral and get a strain energy density. And then we can then get the strain energy, and then we can get 1 with the area instead of line. And we can substitute to get the velocity. And for experiment 1, we want to talk about the curvature, which is the ejection length versus velocity. And so now, let's talk about this. So as you can see over here, the curvature differs. The radius of curvature differs. So we use a 3D printed mold with tubes with different radius of curvatures. And as you can see over here, they all differ in the ejection speed. And so for the data analysis, and this, as you can see over here, this is decreasing in trend, and this is kind of linear in trend. And now for the assessment of the success rate. So as you can see over here, after 6 centimeters, the rate of success drops drastically. And this is due to the buckling effects taking over, resulting in less fracture effects. And as you can see over here, these are the comparisons. And now, let's talk about the discussion of the theoretical relation. So this line is a theorem, and these dots are the datas. And so as you can see over here, there are deviations. And this is the energy loss from the fracture, where we cited the Griffin's theory of fracture over here. And now, for the experiment 2, which is the initial length versus the ejection. And so, we use different lengths from the same bag of spaghetti. And so this is the result. As you can see over here, it seems to be no relevant. However, for the length and the R, which is over here, have the major influences. And so the ejection length is only dependent on the accelerator rather than on the spaghetti. And the ejection length has little correlation with the natural length compared to radius of curvature. As you can see, what we consider is that this is the natural length, where we insert, and after it is ejected, this one ejected out is the one that we consider as the ejection length. And now, the results of a velocity. As you can see over here, this is decreasing. However, this one is increasing. And as we mentioned earlier, the error bars are due to fracture. And also, for this one, there is difficulty for the Lego pusher to push spaghetti into the accelerator, as the spaghetti has been too short. And now for experiment 3, where we talked about the tube thickness and ejection length versus velocity. And for the methodology, as you can see over here, we use different openings, where the radius of this opening is different. So the opening that I'm talking about is the one over here, which is the track that spaghetti will be inserted in. And so for a different thickness, as you can see, we will test on our assumptions. So this is the experimental video. As you can see, they seem to vary in their ejection speed. And this is for the analysis. As you can see over here, the width to ejection velocity it influences buckling decreasing speed. I pressed the wrong button, sorry. And here, as you can see over here, there's 2 0 cones. And these are due to the fact that the spaghetti just directly passed through, as shown over here. So it's not even bending, not even buckling, not even having fracture. It just directly passed through, as the radius of this entering space has been too large. And now for the theoretical relation. As you can see over here, this is a linear line. So there's a linear correlation. However, as you can still see over here, the variations still exist, as this is due to fractures of probability line. And for the nodule, a clear linear correlation exists between the speed and the square roots of 1 over L prom, where L prom has been mentioned earlier. And when the thickness is too large, spaghetti will directly pass straight through the accelerator without being accelerated or broken. And there is a strong positive correlation between the radius of curvature, the width of the accelerator, and the length of the ejected debris. And the occurrence of buckling will result in a significant decrease in ejection speed. And now for experiment 4, where we talk about the curved angle. So this is our methodology, where we use different components as parts and connect them to the base plate. and we can thus control the curvature. Right, sorry, we can thus control the angle. And for the data analysis, as you can see over here, this one peaks at 75 degrees, whereas the lowest one is 90 degrees. And for this angle to ejecting length plot, you can see over here, 70 degrees seems to be the lowest, whereas the 60 degrees one seems to top. However, we can observe no direct correlation between what we said earlier, the angle, and our results. So there's no clear correlation. And so now let's talk about the normalization. So these are the determination of the factors relationship with it. So now for the conclusion. So we answer key questions which include what is spaghetti breaks. And so we say it's due to fracture caused by tensile pressure. And what makes the ejecting speed so high, we answer by saying the ejecting speed is high because the energy of tensile pressure is calculated by linear elasticity theory and is significantly bigger than buckling. And so for here, you can see these. And also, is there anything special about the debris? We come to this. And now, that's our explanation. Thank you.
Okay, so I would like to ask page 7.
Page 7?
Yes.
Okay.
How do you make sure the exclusion is the same velocity?
Oh, so we use a Lego machine and also we use the particle force sensor.
Okay, and did you consider the humidity in the air and also the moisture inside?
Oh, so let's put in appendix, which I think we will put that in discussion.
Okay, and how do you define the curvature in your experiment result? Is it the curvature of the accelerator or the curvature of the spaghetti?
Oh, so the curvature here we are mentioning is the curvature of the mold. And so this is the curvature of the mold.
Yes.
And if you really want to know about the curvature of the spaghetti, we'll put that in appendix.
Oh. In what? In what?
Appendix.
Do you think the insert position will affect your result? Like, since you didn't explain the insert position, like the angle or where you insert it into the center.
Or can we make your question kind of shorter or simpler for me to answer?
Okay. Do you think where you inserted the spaghetti will affect your experiment result?
Oh, so yeah, and so we use we use a machine over here, as you can see, to insert the spaghetti.
I asked, do you think it will?
You mean like which one affects?
It's like the real-life side of the tube. The tube is like this, and then you insert it into the position.
You mean this one?
Okay. Maybe we can start.
start.
So they focus more on the why spaghetti breaks and what makes the velocity so high, and is there something special about the breaks in their main focus. And this is a brief summary about the reporter. Their theories is about the buckling assumption and the fraction theory, and the linear elastic theory. And their experiment is about length vs extraction and curve angle vs the extraction speed and the length and also the angle of the accelerator that will affect the extraction speed. And their data analysis is that they found out that some angle and some width of the accelerator will make the spaghetti not to be ejected. And their conclusion, they didn't have enough time to talk about the conclusion. And this is a pros and cons about the reporter. They have loud and clear voice, and they have clear charts and have enough experiment parameters and data. However, their page number sometimes is too small to be recognized, and they have bad time management. And this is the point I'm going to discuss with the reporter. We want to discuss the moisture of the spaghetti and the curvature of the spaghetti or the accelerator, and the insert point and the inserted point, whether it will affect the result or not. Okay, so I think you can jump to the next stage. First, I want to ask you about the curvature of the your theory. I think you assume the curvature as the curvature of the spaghetti.
That is the whiteboard.
Thank you.
And so, as you can see in our accelerator, this is a track, or what do we say, the tube.
Maybe you use this.
Oh, okay. And so this is the tube. Back water. Okay, so when we insert the spaghetti inside, it will actually kind of stay with it. So here we go. Also, you can use that one.
No, use that one.
So you assume that.
So it's like over here.
So you assume that the curvature of the spaghetti will totally fit this curvature.
As when we use 1R. When we use 1R. And if we are not using 1R, then it will have.
What do you mean using 1R?
The same diameter.
Oh yes.
When we use the same diameter, it will be the same. However, if we don't use, it will be not like that. However, that's just moving back to our theory. We didn't use the curvature in our theory. So the curvature, we're only discussing about the accelerator's curvature, but we are not using the curvature of the spaghetti in the theory. So I would like us to stay towards the report.
Okay, so do you think the inserted point will affect the result, since there are two rely side on the...
Oh yes, as the insert point will affect the results, as there will be some sort of energy dissipation.
So again?
Energy dissipation.
Okay.
Yes, and so it will cause energy dissipation.
So how do you control it? Is it you always insert it in the
Yes, we always insert the same angle as means of for the
No, I mean the different side, like you insert it here or insert it here. How do you control it?
You mean like this one or this one?
Yes.
Oh, so we use a Lego machine as I pointed out earlier. So we use the Lego machine to insert it into, and when insert it, it will bend like this.
Also, you think it will bend like this? Okay, I get but okay, so can you draw the force this spaghetti or gets?
Where is it?
This one is the spaghetti. And can you understand it? This one is the spaghetti.
Yeah.
Can you draw the force that the spaghetti will get?
You mean like when I insert into it and the force that I will get? So first of all, okay. Oh.
Yes. And so you consider that if the spaghetti will be like this, and you will get three different forces. And in this part,
we've already identified over here. As you can see here.
Well,
So this one is the force over.
so you think there is no force in here and here?
No. Oh, please look at the diagram.
Yes.
So here is the sigma of L,
Yes.
which is what we
But as your
said.
diagram, you only have force here, but no force in the contact point here. Yes, is it?
So let's move back to this one. So what we say there is actually like this. So when we insert here, as you can see over here, when we insert over here, what we will experience is the force, right?
Yes.
And as we can see over here, there will be a pressure over here and a pressure over here. And this pressure is the one of insertion.
No, I think you didn't get my point. I think in your diagram, you think the force will come from here, and in the contaction between the spaghetti and the accelerator, exactly, it has three contact points in this diagram, right? Here, here. So how can we do this?
Oh, so as you can see over here, what you mentioned earlier is that these three contact points, right?
Yes.
And so this one is the contact point A that you were mentioning. So this one that you were mentioning over here, and here, and here. So you said these three
So
points.
do you think that
So these three
force-
points, wait a second, please.
Okay.
Let me explain. So this is the point that you tend to say over here, right? And also, this one, as you can see, this one and this one, they are the ones that you are trying to mention over here.
Yes.
So, as you can see over here, this is what we have expressed in the diagram.
Okay, so but for the reporters for the opponent's personal thing, I think that you should consider two types of situation that the spaghetti ball gets different numbers different amounts of force that during the experiment.
However, as you can see, when we are, let me use this one. When we are trying, so first of all, I want to express that energy cannot be calculated twice. Energy is, there will only be one energy, the outcome.
Yes.
And so also, when we are trying to insert the spaghetti into it, there will only be 3 points of contact.
Yes.
And so 3 points of contact indicates 3 points of force.
However, it will cost like one kind of tension and two kinds of tension. Since it has only 2 contact points and 3 contact points that you didn't consider it about.
Pardon?
Yeah, so like in this two different diagrams,
Yes.
it has only 2 contact points and it has 3
Oh,
contact
because
points.
this is the initial insertion. And this is the time.
No, and this one is that you insert it with an angle like this. And this one is you insert it vertical with the accelerator. So when you insert it inside this one, it may be not touching the other side of the tube like this. So you will only get two.
Oh, so you're suggesting that this one will be non-relevant in this diagram?
No, I suggest that you should consider the 2 different situations that will appear in this experiment.
Oh, so you're saying that when we are inserting like this, and so it will only have this one and this one, so it will like have this one and possibly this one moves over here and without this
Yes,
one?
it will be 2 situations that you will need to consider about, but in your theory you didn't consider about. So that's the opponent thing that you should improve it. So you agree with me? Okay, so I'm going to talk about. So do you agree with me? Or we can move to the next one.
Okay, that's fine.
Okay, so since in your experiment you didn't do experiment about moisture.
Oh, moisture. Okay. That's what should moisture slide? So the moisture slide, we'll put it into our appendix. So as you can see over here, this one is simple to dry spaghetti, and this one is
okay,
spaghetti.
I see. But how do you define the soaked spaghetti and the dry spaghetti?
So we dip it into the water.
For how long?
10 seconds.
So do you think that the moisture in the spaghetti will be uniform or not? And since that you only strip it into 10 seconds, and that will inside of the spaghetti will not be.
So that is the reason of the error. As you can see over here, there's an error. So after multiple trials, we can see that there will be error occurring, and that is what you just mentioned. The possible error, the
So
possible
you only do
deviations.
two kinds of experiment, that dry spaghetti and the soaked spaghetti.
Yeah.
So, but I still want to clarify that you didn't identify the uniformity. You didn't identify the moisture in the spaghetti since it wouldn't be uniform.
But the moisture is the same in the same experiment. So for the previous slides, when we were using spaghetti, we just directly kind of like make it dry. And after dry it, we apply experiments under controlled conditions.
Okay, so can you please draw a graph about the moisture and the y-axis is the how much of moisture can you get by? Second, like if you drip it into water for 10 seconds, 20 seconds, and here is the reactance.
So you mean that the effects of the moisture and stuff?
Yes, can you draw it?
Okay, so as you can see over here. Okay, so as you can see over here, it will look like this.
However, the opponent thinks that it should be like this and decrease the sudden critical point. Because the opponent thinks that as the spaghetti become moist, and it can consume more elastic energy. So as it breaks, it will result in much higher. However, as the moisture becomes too much, it will become too soft to eject.
But when you add moisture towards the spaghetti, the mass will increase. The mass will increase drastically with it.
But however, it will get more elastic energy, and that will.
No. But what we said earlier is that it will turn into bubbling, and when it turns into bubbling, it will have lower.
Yeah, so it will turn into bubbling.
And also,
and in the bubbling, if you turn it to the bubbling, it will not eject, and it will get the zero.
But however, what I want to mention is that wait a second, but you said zero the speed, but this one's dropping.
Oh, I make a mistake. I think.
Oh, so you were saying that? Oh, I see.
So do you agree with me?
So
The speed will be zero, and the speed will be zero as. I think the speed will be zero as the moisture increase and the speed.
pardon?
Okay.
Time's up. Component.
Oh, okay. So in the discussion previously, we discussed about the moisture that will cause the ejection speed and about how the inserted point will impact the result. So, however, in our discussion, the opponent insists his point and didn't give me chance for me to clarify my point. I think that is some about with me and the opponent, and so I think this is my discussion.
Okay. Review text of law.
Okay, so first I want to ask both the reporter and the opponent. What is the dominant factor that will affect the ejecting speed of the spaghetti?
The conversion of the accelerator.
Okay.
I agree with the reporter.
Okay. And also, I want to ask the reporter that pay attention to page 13. you can see that when the spaghetti breaks here, so maybe you will have collision with the wall of the tube, right?
Yes.
And will it be energy losses in the collision?
Oh, yes.
And then how do you?
However, though I think that it will exist, but still in our experiments, when we stage our experiments, it does not exist. So it was clarified in the one with the angle part.
Okay. And also for the recording, how do you measure the Young's modulus?
How do we measure the Young's modulus? So we did a curve, and so as you can see over here, this E is the Young's modulus.
Okay. I want to ask both of you, will the pushing speed affect the result?
Yes.
Pushing speed.
Yes. And so we use a slow model where we inserted the spaghetti in with a relatively slow speed. Using a Lego motor where it will insert it into an accelerator under a low speed. So there will be a very low initial velocity.
Okay. And how do you define the R in your experiment? The radius of the curvature.
You mean which one? So you mean the one that I mentioned earlier, the R that I mentioned? So that one is defined as the curvature of the accelerator.
In the inner one or the outer one?
The outer one. As the inner one has no effect in accordance with the theory. Other theories.
Okay. Thank you. That's all.
So now it's the declaration time.
They have compute the their process, they compare between theory questions and also the experiment data. However, they lack of the theoretical line and also lack of quantitative explanation on error and theoretical values. And they didn't have demonstration video and no page numbers. And here's the overview of opponent. They clearly explains why they disagree with the report's opinion. Here's the missing point in discussion. So the first one is the relationship between collision angle and the ejecting speed. And the second one is rotation of the spaghetti degrees. Third one is measurement of the Young's modulus. And the fourth one is contact points of the spaghetti. And here's the discussion part. So the opponent asks that will the insert point affect and did you control the insert point? The reporter answered that it will cause energy dissipation, and they use Lego machine to push, and we agree with the reporter. And the next question, the opponent asked that is there 3 contact points, and they think reporter should consider 2 situations. And the reporter answered that they show them in the diagram, and energy cannot be calculated 2 times. And our opinion is that the number of contact points will also cause different force, and maybe both of them should be more clear on what they are discussing. And next, the opponent's question is that the moisture of spaghetti, the definition of soft and dry. And the reporter answered that they drip into water for 10 seconds and they consider it into error. And our opinion is that we think there are better ways to quantify the moisture. And the center of spaghetti will still be dry and cause the force to be different. And here's our discussion between the reporter and also the opponent. I asked that if you think, I asked that is there collision with the wall of the tube? And the reporter answered that it will cause energy loss. And our opinion is that it should be considered in their experiment data. And how to measure the Young's modulus. The reporter answered that they use the first sensor to measure it. And our opinion is it shouldn't be measured by pushing. And what will cause the energy loss in the experiment? And our opinion is that the first one is the collision between the spaghetti and the wall of the bend tube. And the second one is the friction between the spaghetti and the tube. And next is will the pushing speed affect? And the reporter and opponent both said yes, and I agree with them. Thank you.
Opponent，我们有很多句吗？Oh, it's a reporter.
So I'm a reporter from Team Black Rangers, and this is my concluding remarks. The opponent mentioned about the curvature. However, the spaghetti critical curvature of spaghetti breaking is no correlation with the extraction. The curvature, which is the spaghetti accelerator, that influences the ejecting speed and the brake. The opponent mentioned about the force at contact points, which is same as our diagram. Our model of linear elasticity theory calculates energy of the entire spaghetti, which is suitable for both cases. And the Young's modulus is modeled for remarking parts. And a collision is not observed in experimental videos. And that will be my concluding remarks.
Now, the reviewer, please take the floor. So it's a theory time. Okay, so.
I have a question for the worker. Does the material of the tube will impact your result?
Pardon? I'm sorry.
Does the material of the tube will impact your result? Because you're using the same model.
Yes. So I'll say yes.
What kind of change?
Because of friction will cause the energy dissipation. And so in our model, we used 3D printed models throughout the whole process, and we used the same material, so it is not mono.
If assume, I just assume, if the tube will change it to another kind of material, then is your linear theory still valid?
I suppose yes. If not, if the tube is not soft in what is that what we described it? Because if it is soft, or how can we say this? Like when it is soft, it will have much more energy dissipations, and it's like kind of like what happens in elastic collisions. Kind of like that sort. So it will have an uneven curvature and other sorts of errors inside, according with my assumptions.
Even the questions, shouldn't your answer be that if with different materials, you will change the elastic properties, right?
Oh, yeah.
Now the elastic property you mentioned, and also the reviewer, is that the Young's module. But that's not the only. It's not the only important factors. You also show a factor which is called EI. You didn't specifically say what it means, but I read it. I is the moment of inertia sort of thing, right?
Oh, yes.
Yeah. And then in the chart, your linear theory, you just say that's the Young's modulus.
Oh.
Is that consistent?
So it's like we calculated the EI, and so
You calculate.
I fitted it.
Yes.
We fitted the EI, and so we can get a slope of EI. And so E is the Young's
Okay, I
modulus.
just want to make sure that it's EI. It's,
Oh, sorry.
you say that's Young's modulus.
Sorry.
I don't quite see. But the answer should be those properties determine the outcome because they determine also the energy. Now, no further question. I want to ask about this point of insertion because it's a heat debate. For some aspects, it's the force point of application important. Considering that you are using the energy conservation, that the stress energy released is transformed into, say, kinetic energy. Is that right? You didn't study the dynamics of kinetic force. Is only mean when you're studying the dynamics. That's how it moves out of the tube. Isn't that correct? Force is not necessarily important.
Pardon?
I'm saying you're using an energy method primarily, right? For say in discussing the speed of the injection, right?
Yes.
Did the opponent agree?
No, but I assume that with 2 contact point and 3 contact
No. We're discussing their experiments, not the.
Yes, but I don't agree because.
You don't agree that they're using the energy method?
Yes, I agree, but
Okay.
I have.
No. My point is that we should, based on their method, but their method use energy, so I'm not quite sure how important it is to.
I mean that different contact point call.
Because we have specifically asked to check if the result shows how it moves inside that dynamics, but I don't see this important data part. Your question is more related to that. That is, if you want to study what's in the motion inside the what you call bed tube, then you do need to consider force. Okay, we use our time. You only have 5 minutes.
Are we ready?
Yeah, I'm ready.
So let's show us all.
Thank you.
Now the score for reporter 77678. And score for opponent 66677. And score for reviewer 76667.